Let's start our lecture. The theme of our lecture is the solution of boundary problems of the Laplace and Helmholtz equations by means of Green's function. I remind you that the previous lecture we stopped at the following point, namely we found from the Green's formulas that the following equation holds. Where U and V are doubly continuously differentiable functions. So, if you denote as L the following operator, in fact it is the operator of the Helmholtz equation, of Helmholtz operator, and define or denote as G0 be a principal fundamental solution of the operator L, that is, it satisfies the following equation. And in fact, we wrote the explicit form for this operator on the previous lectures. And G0 was given by formulas 7.3 and 8.3. Okay, it is for Laplace equations, this formula, and this formula from our previous lectures is for the Helmholtz equation. Then we can write this equation 12.3 as follows. I denote it as 12.4. Then take V to be equal to G0. Then, as follows from this equation, we have, using this property, when we substitute V into the left-hand side of this equation, this transforms into delta function, and as integration over x can be easily carried out, and so we have I remind you that gamma is a boundary of D. It can be denoted as follows. thus we have the following relation. 12.5. And in fact, this formula represents an integral form of the solution of the following equation. L is equal to G, and here are some boundary plus some boundary conditions. As we see from this formula, that the value of the function u at the point x0 is determined by the first integral. In fact, g is a known function, and large g0 is also known explicitly. So this integral is known. And here we have some integral over the boundary of the domain D, and the values of the function and its derivative are also assumed to be known on the boundary, and these functions, the gradient of the function g0, are also known. So the right-hand side of this equation is known, and we can found by evaluating the integral the function at arbitrary point x0, which belongs to the domain D. Now we slightly simplify this general form, or rewrite it in a more convenient form, and adjust it to the particular problems, namely to the Dirichlet and Neumann problems, Neumann boundary problems. So let V0 is a general solution, be a general solution equation to the homogeneous equation of Laplace or Helmholtz. And in this case, as follows from (12.4), we can write this will be 12.6. Now we consider, we subtract (12.6) from 12.5 and obtain the equality where we denote as gx slash x0 the following combination. Namely, we obtain the index, the operator number, reflects the variable with respect to which the derivative is evaluated. So we have the following equality, and obviously that follows from this definition. That this function satisfies the equation for the fundamental solution. In fact, it's just another one fundamental solution for the Laplace and Helmholtz equation. Because it differs from the principal fundamental solution by the solution of a homogeneous equation. And this equation is as follows. And so, if we consider the solution of homogeneous equation, then we can write but in the general case, that is when we consider the homogeneous equation. Then we have the following formula. Right. So I remind you that there is a large ambiguity in defining this function because we can subtract an arbitrary solution of a homogeneous equation. And in what follows, we consider some particular choices of this function in order to simplify this formula, this or that formulas, and to adjust them to the solution of a particular boundary problems, Dirichlet boundary problem and non-boundary problem. Okay. So let us start with the Dirichlet boundary problem. Let us suppose that the function g satisfies the following boundary condition. That is, on the boundary gamma, it is equal to 0. Then this function is the solution of the following boundary problem. In fact, it can be considered, this equation can be considered as equation on the solution of the homogeneous equation V0, which appeared now. And definition. The solution of this system of equations is called Green's function for the Dirichlet boundary problem. For such a choice of the function g, which is called the Green's function, this expression, the expression for the solution of the Gельmgольца Laplace equation can be written as follows. So, if we have, in that case, if we have the Dirichlet problem, remind you that it looks as follows. And then we can write the solution of this problem explicitly in terms of integrals. Thus, if you know the corresponding Green's function, then we know the solution of the Dirichlet problem. So now we turn to the Neumann problem. I remind you that it is formulated as formulated as follows. This is the derivative along the normal to the surface gamma at the point x. And so let us impose the following condition on the function, the following conditions on the function g. The fundamental solution that it satisfies this defining equation, and also it obeys the following boundary conditions. Then, as follows from the general formula, 12.9 or 9 prime, we can write due to the fact that the gradient of the function u is multiplied by ds, by the element ds, we have to the scalar product is equal to this expression. And so we can write eventually get 12.16. So definition. The function which satisfies equation 12.16 is called Green's function for Neumann boundary problem. And we saw that the solution for the Neumann problem for Dirichlet or for Laplace or Helmholtz equation can be written in terms of this Green's function as some integrals. You see here, which is formula 12.18. It can be easily proved that these Green functions are symmetric. Consider, for example, the Green's function for Dirichlet problem. They're symmetric, that is, they satisfy use this relation. And let us prove it for the Dirichlet Green's function. Let us take u is equal to this function gx slash x1 and v is this function. And in formula 12.4. Then we have the following inequality, which in fact is consequences which follows from the Green's formulas. So what we have? So we have the following relation. Now we use the fact that G is a fundamental solution, and we can replace this combination by the delta function. This one. These delta functions remove integration, and so we have. And so we see that the Green's function is a symmetric function of its variables. And remark, in all the above discussion, the domain D can be of an infinite volume. Bounded, and all the formulas hold, but in this case we have to guarantee that all the integrals are convergent. The integrals over D or along gamma should be convergent. Consider the following example. Which of course you know from the course of general fields, but we formulate this example in more mathematical terms. Point 1, just called it as Green's function for the Laplace equation in a half space. Where the whole three-dimensional space is split into two parts by some plane gamma. We can choose this plane to be defined by this equation. And so we need to find the solution of the problem. G is a Green's function for the Dirichlet problem. Looking at a picture. It is a plane gamma. Here is some point R0 and R0 prime, its mirror image at this point. And so we have to find the solution of this problem for x belonging to D, where D is a set of points three-dimensional space is positive net. Thus we have to find this function in the R half space. Then we apply the following trick. Consider the function, the following function. Oh, excuse me. Here is x0, x0 prime. Consider the following function. Let me write coordinates of this points x0 prime, the image of the point x0, which is obtained from the point x0 by reflection in the mirror gamma. It's mirror image. And so consider the following function. We know from the previous lectures that it satisfies equation due to the fact that x0 prime doesn't belong to the region D, then the right-hand side of this equality is 0. this function is a solution of homogeneous Laplace equation. And then we can construct the function g which satisfies this system of equation. Namely, let us consider the following combination. The first term is a principal fundamental solution of the Laplace equation, and the second term is just this particular solution of homogeneous Laplace equation. So when we act on the function, when we act by the Laplace operator on this function, we obtain points lie in the upper half space because it goes to 0 and it gives rise to the delta function. And let us check that this function satisfies the second condition. There is that is equal to 0. Satisfies the second condition. We consider the points at z is equal to 0. Rewrite this equation, this formula in more explicit terms. And we have to put here z is equal to 0. Now it is obvious that this term equals to this term, and so when we subtract from this term this one, we have 0. Thus, this function does provide us with a green function for the Dirichlet problem. And we can use this function to construct the explicit solutions of the Dirichlet problem, of an arbitrary Dirichlet problem, and in terms of integrals, as it was written in general formulas at the beginning of our lecture. Now, the next example. Remark. In fact, if we consider some electrostatic problem, then this function, Green's function, possesses a physical interpretation. Namely, it gives the potential of a point charge located at the point x0 near the mirror gamma, or ideal conductor, mirror is the ideal conductor. Gamma is defined by this equation. So the next example. And it is called the Grina's function for the Dirichlet problem of the Laplace equation for disk and ball. We will consider only the case of a disk, and as for the ball, I will give only the final answer. And the proof of the formula for the Green's function is performed along the same lines as for the disk. We will consider only this case in detail. And as for ball, the final answer will be also only given. So, consider the two-dimensional Laplace equation. Is written as follows, and we know that the principal fundamental solution of this equation in two dimensions denoted as G0. It is given by the formula. And in accordance with the general theory, which was explained at the beginning of our lecture, we have to find the solution of homogeneous equation such that the solution of homogeneous equation here D is a disk, some radius D, a set of points, some radius R, some radius R, and so V0 should satisfy the Laplace equation with the disk D. As denote is gamma the boundary of D, but of course it is specified by the following equation. And this function should satisfy the another one equality. Namely, we require that provides us with the Green's function for the Dirichlet problem. thus we have the following equation. That is, this Green's function should be 0 on the boundary gamma. Okay. The idea to solve this problem is somewhat similar to the method explained in the previous example, but which has to be generalized to the case of a circle instead of the plane gamma. Let me draw a picture. There is a point x0. We can construct the point x0 prime by means of the construction known to you from the course of conformal mappings, and this function, this point is called symmetrical with respect to the circle gamma. It's a symmetric image of the point x0 with respect to the circle gamma. And we discussed such a construction and such points in the previous semester of our course. So we have the following relations. There is R0, the absolute value of x0, R0 prime, the absolute value of x0 prime, or the radius of the circle, and we have the relation by definition of this point. And so this relation can be written in the following form. Thus, the two triangles x1. The two triangles are similar. By two sides and the angle. And the common angle. Therefore, we have the following relations. Now consider the following function. V0, and in fact we will have to prove that this function satisfies these requirements. Written here. So this function is given by the following expression. Declares that if x0 belongs to D, then x0 prime doesn't belong to D. Then we declare that, okay, let me continue our lecture. So this function is in fact a solution of homogeneous Laplace equation. You can see from the following obvious equality. It is just a constant. And so under the Laplace operator, it goes to 0. It vanishes, and we have only this contribution. But when the Laplace operator acts on this combination, we saw that the result is given by the delta function, but x prime 0 doesn't belong to the domain D, where x runs, and so we have that this delta function is in fact 0 when x is from B. So this solution of homogeneous equation, and we have to check that the following equality holds when the function v0 is taken in this form. Now let us check this condition. Consider this function taken on the boundary gamma. The point on gamma we denote as x1. And using the above relations, we find that this function on the boundary gamma is equal to the principal fundamental solution, the Laplace equation taken on this boundary gamma. Thus, we obtained the Green's function for the Dirichlet problem with the boundary gamma. With the boundary gamma, and gamma is the circle in the plane. As for the ball, we have the following Green's function. And this is, excuse me, it is a complete answer for the circle, for the disk. Let me write it explicitly. So, and as for the ball, consider the following ball, and then gamma is a sphere. And Green's function using this reverse. Where x0 prime is a point symmetric to the point x0 with respect to the sphere gamma. And in particular, the following relation holds. And these 2 points lie from the same ray emanated from the origin of the system of coordinates. Thus we have the following picture, as in the case of a disk. It is a sphere. Here is a point 0, this point 0 prime, and the following relation holds. Satisfied. Thus, we have the solution, we have the Green function for the Dirichlet boundary problem. And in fact, of course, in the course of general physics, you know such a method as an image method for construction of solutions of some problems in electrostatics by using the images of the charges in the conductors. In our case, such conductors were plane, into the conducting plane, or a circle, or in 3 dimensions it is just a hollow cylinder, either conducting, and in this case it was an either conducting sphere. And of course, the Green function, for example, this Green's function possesses the same physical interpretation as it was for the Green's function for the Dirichlet problem in the case when the boundary gamma was a plane. That is, this Green function is the potential or the electric field. For the following problem, we have a point charge, it's a point x0, and we have a conductive sphere, and the problem is to find the potential inside of this sphere. And this Green function provides the solution to this problem. So, the next paragraph. The solution of the Dirichlet problem for disk and ball. previous section, we constructed the Green's function for these problems. Now we can, by the use of the general formulas, which were given at the beginning of our lecture, we can construct the solution of the corresponding Dirichlet problems and general solution in terms of integrals. So, at the beginning, we consider the problem for the disk, and as for the ball, I will give only the final answer in terms of integrals. So, let D be a disk defined by the form of inequality. And gamma, which is a boundary of the disk. Specified by this equality. And we consider the following problem. It is a Dirichlet problem, as you know. And we know that the solution of this problem is written in terms of the integral. This formula was given on the first part of our lecture. And the explicit expression for this Green's function was also found in the above examples. Here. The point x prime 0 it is a certain function. The point x0, it is a point symmetric to the point x0 with respect to the circle gamma, as it was explained in the previous example. And in fact, in this paragraph, we just simplify this expression. That is, we substitute this Green's function to this expression, we lay it in gradient, and then we rewrite this integral in some useful form. And this integral will be called as a Poisson integral. So let us start to perform this program. And let me draw a picture. The circle gamma. The point 0. So point x0 prime, and this angle theta. So we will need the full notation. 0, x, so it's x 0 prime. And here x is an arbitrary point on this circle, and x 0 prime is the image of the point x0 in the circle gamma. And the point x runs along gamma in this, in fact, in this interval. So we have the following properties or relation. A consequence of the fact that x belongs to the circle gamma. This is in fact a definition of, it follows from the definition of symmetric point. And we have the following relation. Good. By using the definitions of rho 0 and rho 1, this can be written as in such a form. Let us prove this relation. Definition of the scalar product, we have the following quality. Then consider the scalar product of such a form. I just write a sequence of equalities and then explain where they come from. Eventually, so can be written in the form in the first equality, we just multiplied, we just expand this scalar product. And we can write in this form, and the square of x is equal to r squared, and so on. Then we use this relation, property 2, and we write it in the following form. Then then we express R0 by using this property in terms of large R and small r prime 0, and just write in this form, and let's see that it is just a square of the scalar product, a square of the vector x minus x 0 prime. And thus, comparing this and this one expression, we see that it is just the property 3. And the fourth property, the formula for derivative of the modulus of the vector, which of course we know, but I'll write it here. Then we have all the formulas that are needed to simplify this expression. But first we consider the gradient of the Green's function. Then we have these relations, and in fact this logarithm is a constant, so its gradient is 0, and here we differentiate the logarithm by the standard formulas, and the last equality we used the property 4, and then form scalar product takes the form using property 3. Can write it in this form. And then we come to the full expression. The next step, we have to simplify these scalar products in some convenient form. Consider scalar products separately. Then, using the definition of rho 0 and rho 1, we have Olber's relation, which can be written in this form. Then multiply these two expressions by r squared and r0 squared. Okay. We multiply this expression because here this expression enters with these vectors. Then the expression in the square brackets is equal to and so we have here the point x0 is fixed, belongs to B and fixed, and x runs along Let us introduce the polar coordinates. Way as r and phi. Then the point x0 possesses some coordinates r0, phi0, and the point x has the coordinates large r and phi. It's clear that the angle between the two vectors x0 and x is equal to theta, and it is equal to phi0 minus phi. It is also clear that this system of coordinates ds is equal to r times d phi, and then we can write the solution of the Dirichlet problem taken at the point r0, phi0 in terms of the form integral. All the quantities are known here, and we just substitute them to this integral. And excuse me, here function f, which depends on the point x, and the coordinates of the point x are large and fine. So we have to integrate this. We have to take this integral with respect to phi. We can write the following form. Definition. The function e x at 0, which is by definition is equal to the following expression. Is called the Poisson kernel. Definition is finished. Then, in terms of this kernel, we can write the solution. X runs along gamma. Definition. The integral 14.3 is called the Poisson integral. Thus, we have found the integral representation for the solution of the Dirichlet problem in a disk, and we can find this solution at arbitrary point with coordinates r0, phi0 by means of with the help of this integral, just evaluating this integral. In some cases, it can be evaluated exactly in terms of some known functions, but in general case, of course, one has to evaluate this integral numerically. But nevertheless, this integral representation, of course, useful, and we will use it to prove some properties of this function. Okay, consider now the analogous problem for the ball. As for the ball, the solution has the form 14.3, but with some changes in notation, namely the elementary area of the sphere is equal to the standard expression, this theta belongs to this interval, and phi is from this interval. And the Poisson kernel is written in the form where gamma is the angle between the vectors x and x0. Now let us find the explicit expression for gamma in terms of coordinates of the vectors x and x0 in the spherical system of coordinates. To this end, we write the following standard expressions. Okay, let me stop at this point, and in the next lecture we continue this the investigation or solution of the Dirichlet problem. Okay.